Probability is not about guaranteeing specific outcomes, but about estimating the likelihood of events. It quantifies uncertainty, offering a mathematical framework for modeling chance. However, real-world randomness is rarely perfect due to factors such as imperfections in systems or measurement errors. For instance, flipping a coin theoretically gives a 50-50 chance of heads or tails. Yet the flip's outcome can be influenced by subtle factors like air resistance, the force of the flip, or slight asymmetries in the coin itself. These factors introduce tiny biases, making the actual probability deviate from the theoretical value. Example: if a coin is slightly heavier on one side, it may land on that side more often, creating a small but consistent deviation from a perfect 50-50 split over many flips. Analogy: it's like shooting arrows at a target with a slightly bent bow. The theoretical aim is perfect, but small imperfections in the bow skew where the arrows land, reflecting how probability can be influenced by subtle, real-world factors. In practical applications, probabilities are estimated using finite samples, not infinite repetitions. This introduces sampling error, where results deviate from the true probability simply because the sample size is too small. Even with large datasets, randomness can create temporary clusters or streaks that make patterns seem more significant than they are. Example: tossing a coin 10 times might produce 7 heads and 3 tails, giving the illusion of bias. However, over 10,000 tosses, the ratio of heads to tails will likely approach 50-50. Analogy: it's like tasting a spoonful of soup and finding it salty. The whole pot may have the right balance of flavors, but your small sample doesn't represent the larger truth. Many systems are deterministic at their core, but behave in ways that appear random due to chaos and complexity. Small, immeasurable differences in initial conditions can lead to vastly different outcomes over time, a phenomenon known as sensitive dependence. This unpredictability is common in weather systems, lotteries, or even stock markets. Example: a lottery machine uses tumbling balls to generate random numbers, but if the starting position of the balls or air pressure changes by even a tiny amount, the result may change drastically. Analogy: it's like predicting the path of a leaf in a swirling wind. The movement is governed by physics, but the vast number of variables involved makes it impossible to predict precisely, giving it the appearance of randomness. Pseudo-randomness explanation. Many systems we call random are not truly random. Random number generators, RNGs, used in computers or lotteries rely on algorithms to simulate randomness. These are deterministic and can produce hidden patterns if analyzed over long periods. While they are nearly indistinguishable from true randomness for practical purposes, they are not perfect. Example: a pseudo-random number generator might be used in a digital lottery, but subtle correlations between numbers could emerge if the algorithm's seed or sequence is analyzed. Analogy: it's like shuffling a deck of cards in a way that appears random but follows a repeatable sequence if the same shuffle method is used every time. Mathematical versus physical randomness. Explanation. In nature, randomness is debated. Quantum mechanics introduces probability at a fundamental level, but even quantum events could be influenced by hidden variables we do not yet understand. Physical systems, like lottery machines, introduce randomness through mechanical and environmental factors, but these are ultimately governed by deterministic physics. Example: radioactive decay appears random, but physicists debate whether hidden variables influence when an atom decays. Analogy: it's like rolling dice in the dark. You can't see how they land, so it feels random, but their path is determined by how they were thrown and the surface they hit. What are cold and hot numbers? Explanation. Hot numbers are numbers that appear more frequently in recent draws. Cold numbers are those that appear less frequently or not at all. These trends emerge from random fluctuations and reflect how finite datasets naturally produce streaks and gaps. Example: if a number is drawn 5 times in a row, it becomes a hot number, but this streak is likely just a statistical anomaly rather than a true bias. Analogy. It's like flipping a coin and getting heads 5 times in a row. It doesn't mean heads is more likely. It's just a natural occurrence in randomness. Physics of lottery machines. Explanation. Lottery machines rely on physical processes to randomize outcomes, such as air pressure and tumbling mechanisms. Slight imperfections, like differences in ball weight or machine calibration, can introduce small biases, causing some numbers to appear more often over time. Example. If one ball is slightly lighter, it might be drawn more frequently, creating a hidden bias in the system. Analogy. It's like spinning a roulette wheel with an uneven surface. Over time, certain numbers may come up more often due to the imbalance. Yes, hidden biases in lottery systems can cause trends in cold and hot numbers. Physical imperfections, such as slight differences in ball size, weight, or the mechanics of the machine, can subtly skew results. These biases are typically small but detectable with enough data. In a real-world case, a lottery machine was found to produce more even numbers than odd numbers due to a calibration issue. It's like a deck of cards where a few cards are slightly bent. While the shuffle seems fair, those bent cards are more likely to stick together or be drawn. Random systems like lottery machines are governed by physical laws. Factors such as friction, turbulence, and air resistance introduce complexity into outcomes. Even quantum systems, which are probabilistic, follow physical principles that may reveal deeper patterns. The turbulence inside a lottery machine causes balls to mix unpredictably, but these movements are still governed by fluid dynamics and mechanics. It's like stirring cream into coffee. The swirling patterns look random, but are determined by how you stir and the properties of the liquid. The imperfections in probability and randomness highlight the limits of human understanding. What appears random may conceal hidden layers of order or deeper physical principles. As science progresses, phenomena once thought to be purely random, like chaotic systems, often reveal deterministic roots. The study of chaos theory has shown that systems like weather, while unpredictable, follow deterministic rules when viewed from the right perspective. It's like watching waves on the ocean. They seem random, but they are shaped by wind, tides, and underwater currents, all governed by precise physical laws. Probability and statistics are inherently imperfect because they rely on approximations, finite data, and human interpretation. Hidden patterns such as hot and cold lottery numbers arise from physical biases or chaotic processes, reminding us that randomness is often a reflection of complexity beyond our current understanding. These imperfections may one day reveal deeper truths about the universe's interplay between order and randomness, hinting at a reality where even chance has hidden rules waiting to be discovered.